Hey guys, Mr. Keener here with another video recording, this time for Unit 2, Lesson 3, Solving Quadratic Linear Systems Graphically. Let's go ahead and get started. Alright, so before we get started on quadratic linear systems, we need to talk about what is a system of equations in general. So a system is a set of two or more equations that use the same variables. So here's an example here. We have two equations that each use y and x as their variables. Now, to solve a system of equations is just like solving any other equation. We're looking for values for the variables that make the equation true. But to solve a system means that we are looking for values for the variables that make all of the equations true. So here we have two systems. Each of these, two equations. Each of these equations has their own solutions. For example, 1, 3 is a solution for this equation. When x is 1, y is 3. That makes it true. But it is not a solution to this one. If x is 1, then y would be equal to 5, which is not the same thing. Likewise, if this one, if x were 2, y would be equal to 7. But if x were 2 in this one, then y would be equal to 4. So we can see that even though it is a solution to one of the equations, that doesn't necessarily mean it is a solution to both of them. But there is one solution to both of these equations, which is -1, 1. So if x is -1 in this one, -1 plus 2 is 1. And if x is -1 in this one, -2 plus 3 is 1. So this solution works for both of these equations, which means that this is a solution to the entire system of equations. Now we can do that algebraically, but an easier way to do it is actually to look at the graphs of these two equations. So let's go ahead and pull up the graphs of y equals x plus 2 and y equals 2x plus 3. We can tell they're both linear equations. We see the straight line, and they intersect at a specific point. And that point that they intersect, what do you know? It's -1, 1. So the solution to the system of equations is where the two graphs intersect. Now this makes sense because the blue line is all of the solutions to 2x plus 3. The red line is all of the solutions to x plus 2. So the point where they intersect is the only point that appears on both lines. So it's the only point that is a solution to both equations. And that's how we know that that works. All right, let's get started on our guided notes. So to start off, we are going to identify the two types of functions that are graphed on this coordinate plane right here. So we can recognize our shape. We have a straight line here. That is a linear equation. And we also have our tried and true parabola right here. It goes down, then it turns around and comes up. We have our vertex. We have our u-shape. That is a parabola, which means that this is a quadratic function. And since this is a combination of a quadratic and a linear function, we call it a quadratic linear system. Amazing how that works. All right, part B, which point is a solution of the system of equations shown on the graph? All right, so just like in our previous example, the solutions are going to be the points where the two separate graphs intersect. So they're going to be right here and right here. Now, this solution is going to be a little bit easier because it's on the cross here on the actual grid line, so that makes it a lot easier. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8, 9 is one of our solutions. And let's take a look at our choices. That is our first option, so that's going to be it. But just to make sure, let's take a look at these other options. 5, 0. 1, 2, 3, 4, 5. So that is the x-intercept of our parabola. So that is what we referred to as a solution in the previous lesson, also known as a zero or a root, but we can see it is not on this line, so it can't be a solution to that equation as well. So it can't be that one. 0, 3. Now that is going to be on the straight line, but since it is not also on the parabola, that can't be a solution. And then 2, -3. 1, 2, 1, 2, -3. That's just the vertex. They're thinking they're just going to catch you out with the vertex there. All right, so 8, 9 we can see is a solution. There is one more solution, but it's a little tougher to see. It's not exactly on the grid lines, but it looks like x is between -1 and -2, and y is between 1 and 2. So there's some fractions involved in there. It exists. It's just kind of hard to tell what it is without being able to see the equations. All right, let's get into example 1. It asks us to solve this system of equations graphically. Now to solve it graphically, that means, guess what? We're going to have to graph it. So let's get started on that. Let's start with our linear. We know it's linear because we don't see a square. It's just a degree of 1 there on the exponent. So y equals 2x minus 4. We can go ahead and, ooh, not great looking, but we can go ahead and create our table of values. Let's start with 0 when y is 0. When x is 0, y is negative 4. When x is 1, y is going to be negative 2. When x is 2, y is going to be 0. When x is 3, y is going to be positive 2. We can see this is a linear equation, so this follows the pattern of just adding 2 every time we add 1 to x. Easy to fill out those values. Also, we know it's going to have a slope of 2, so let's go ahead and start graphing those. 0, negative 4. So right here, and then each one, we can actually see the pattern. We don't even have to look at our table. We just go over 1, up 2, over 1, up 2, and that makes it nice and easy. So let's go ahead and do that. Now I have the ability to just draw a line on the graph, which is nice, so I'm going to go ahead and do that. Ooh, very sleek. All right. Now, so that's one of our equations, and we have to graph our quadratic equation now, and what we are looking for is where those two graphs intersect. So y equals x squared minus 4x plus 1. So we know that the y-intercept is 1. We can find the axis of symmetry by doing x equals negative b over 2a. Which is going to be, my b value is negative 4, so 4, and my a value is 1, so 4 over 2, which means my axis of symmetry is x equals 2. That's going to be this line right here, this vertical line right here. Now, we like to find our axis of symmetry while we're graphing because we're going to center our graph on that axis of symmetry. Makes everything a lot easier. So let's go ahead and put x equals 2 as our first one. So when x is 2, we can find the y value of our vertex by plugging 2 back into our equation. So 2 squared minus 4 times 2 plus 1. And then we can evaluate that. We can use the calculator or we can do it by hand. This is going to be 4 minus 8 plus 1. So 4 minus 8 is negative 4. Negative 4 plus 1, it gives us negative 3. So it's going to be negative 3 right here. So 2, negative 3. So this is the point on our parabola. Let's go ahead and erase this line right here. If you drew a nice dashed line, that's okay. You can leave it there, but I like to erase it there after I start to actually graph it. All right. Now to find our next value, we're going to go 1 to the left. So when x is 1, y is going to be 1 minus 4 plus 1. So 1 minus 4 is negative 3. Negative 3 plus 1 is negative 2. So it's actually going to be right here. All right. So y is negative 2. When x is 0, well, we already know that the y-intercept is 1. So we can go ahead and put that there too. So y is 1. So that's going to be right there. Now, once I have my axis of symmetry, we've been over this trick before, but I'll do it again. Symmetry means that it's a mirror image on the other side. So if we're 1 to the left of the vertex and it's at y equals negative 2, that means 1 to the right of the vertex is also going to be at y equals negative 2. If 2 to the left of the vertex is at y equals 1, that means 2 to the right of the vertex is going to be at y equals 1. All right, we're going to keep going one more. So let's so 3, negative 2, we see that point on there. And then 4, 1, we see that point on there. We're just going to go one more to the right just to flesh it out. You can use your calculator to create this table. I'm just doing it by hand just to show you how it's done. If you want to watch this on double speed, that makes it easier. All right, so 5 in here, we get 25 minus 4 times 5, which is 20, plus 1. So 25 minus 20 is 5. 5 plus 1 is 6. So that's going to be 6 right here. So at x equals 5, 1, 2, 3, 4, 5, y is going to be 1, 2, 3, 4, 5, 6. Look at that. Okay. So let's go ahead and connect these. I'm going to do my best to create a nice parabola. It looks terrible. A lot easier to do by hand than with the mouse. That's what our parabola is. All right. First question. This system has how many solutions? The number of solutions is the number of places where these two lines intersect. And we can see there's an intersection right here and an intersection right here. So this has 2 solutions. Now those solutions are the points at which they intersect. So one solution is going to be x equals 1 and y equals negative 2. So that's one solution, 1, negative 2. And another solution is going to be x equals 5 and y equals 6. And we can see that those points appear on both graphs, which is why they're both solutions. If we plugged 1 into x for each of these, so we know we're going to get -2 for this one, we did that by hand. If we plugged 1 in for x here, 2 minus 4, we're going to get -2. And that's why that works. It works in both equations. All right, with our next example, we're going to do the same thing. Let's go ahead and graph both of our equations. I'll give you some time to go ahead and graph those now by creating tables, either on your paper or using the calculator, and then put those graphs on the on the coordinate plane to the right. All right, after we've graphed both equations, we can see this is a little bit trickier than the last one. So we can't see a clear crossing between these two. And if we take a look at the graph officially created by a computer, we can see it's even trickier actually. Sometimes these graphs do not intersect in two spaces. Sometimes it's only one space. And we can confirm that by looking at the two tables here. There's actually only one point that appears on both tables, 1, 3. If you zoom real close in the graph, you can see that they touch each other there, but they don't actually cross in any other places. So in this case, this system only has one solution. It only intersects in one particular spot, and they don't even cross each other. They just happen to have that same point on both graphs. All right, so this next example is also going to be a little bit tricky. Take the time to find the values and graph the points. All right, I did a little special effects there to replace the coordinate plane with the fully graphed graph. Now, what we notice that's odd about this particular system is that there is nowhere where these two graphs cross. We can see that the linear equation is going to continue to go up as it goes to the right, but the parabola has long since outpaced it. It's just going to keep going up and up and up. So at no point are these two going to cross, which means that there are zero solutions. Zero solutions. If I put the S out there, I might have given it away. This system has no solutions. There are no points that satisfy both equations. Lots of points to satisfy this one, lots of points to satisfy this one, but none that satisfy both. All right, let's add some real-world applications to our systems here. Let's take a look at this question. A company is considering building a manufacturing plant. They determine the weekly production cost at site A to be A of x equals 3x squared, while the production cost at site B is B of x equals 8x plus 3. So we have a quadratic equation and a linear equation, where x represents the number of products in hundreds, that'll come into play later, and A of x and B of x are the production costs in hundreds of dollars. Graph the production cost functions on the set of axes below and label them site A and site B. All right, so this question is telling us that we have to graph them. So this is not one of those situations where the graph is optional. We must graph each one. So take the time to create a table of values, find your axis of symmetry for 3x squared, and put those points on the axes. All right, so we've graphed 3x squared in the domain that they've specified for us. So they've actually given us the axes here. So we have our number of products from 0 to 4 and our cost in hundreds of dollars, and they've given us a scale. Looks like it goes up by 2 every time. So when x is 0, y is 0. When x is 1, y is 3. We kind of put this data, it's about halfway in between the 2 and the 4 there. It's okay if it's not quite perfect, as long as they see what you're doing here. When x is 2, 2 squared is 4. 4 times 3 is 12. When x is 3, y is going to be 27. 3 times 9. And when x is 4, y is going to be 48. And that's going to fit all in our graph. And let's do our best to try and connect these. Now it also asks you to label them site A and site B. So this parabola is going to be site A. All right, now let's start graphing site B. So site B has a linear equation. We know it's going to look like a line. 8x plus 3, and we're going to do it on the same domain. So we start at 0. When x is 0, y is going to be 3. That's pretty easy. When x is 1, 8 plus 3 is 11. When x is 2, and actually we can use our shortcut, and if we go up by 1 on x, we know we're going to be going up by 9 for y. And we can do our 4 numbers here. 0, 1, 2, 3, 4. 30. Did I say 9? I meant 8. 35. Okay, we can graph those points. 0, 3. Once again, in between. 1, 11. In between the 10 and the 12. 219. It's getting up here. It's going to form that straight line. It should form a straight line. If it's not forming a straight line, then you've made a mistake and you need to go back and fix it. All right, and that's 35. Oops, I kind of missed there. Okay, so we can connect those to the line. Use a straight edge. I used to use like using like a student ID or something as a straight edge if you don't have a ruler on. So here is my site B, and I'll do that in black just to differentiate it. Site B. Now, the positive values of x for which the production costs at the two sites are equal. So that's what we're looking for. Find the positive values of x for which the production costs of the two sites are equal. Looks like it got cut off a little bit. Explain how you determined your answer. So if the y values are the production costs and the x values are the number of products, then the values of x where the y values are the same is going to be right here where the two lines intersect. So when 300 products are produced at site A, that's going to cost $2,700. And when 300 products are produced at site B, that's also going to cost $2,700. Remember the units that we used in the example, in the write-up there. Sometimes we got to go back and take a look. All right. Explain how you determined your answer. Well, we solved the system of equations. We looked for where the two graphs intersected. Part 2, if the company plans on manufacturing 200 products per week, which site should they use? Justify your answer. So here we go. We're at 200 products per week. That's going to be this axis right here. Not the axis of symmetry, but that's what it's asking. 200 products. So if 200 products is how much we're manufacturing, which site is going to cost less? Well, if y is the cost, that means that we want to look at the line, or we want to pick the site that's going to have a lower y value at this cost. So at this point right here, site A is only costing us $1,100. So we'd rather do that at site B. So we're going to choose site A because it's cheaper at x equals 2. Or y is lower at x equals 2 is another way to say that. All right. Well, thank you guys for tuning in. Fill out your guided notes. Write down any questions that you have on the guided notes at the bottom, and we'll answer those in class tomorrow. Look forward to speaking with you about these problems.